Hey, biology students, it's Mrs. Bartlett, and today, day 4, I'm going to tell you all about density-dependent limiting factors. I know, you're excited to hear about this. Calm down, calm down. All right, so yesterday we talked about limited resources or limiting factors, and today we're going to look at a particular type of limiting factor, a density-dependent limiting factor, and how it's related to the spread of COVID-19 and other infectious diseases. So if you look at this it's kind of a graphic, let's say, you can see there's a whole bunch of little frogs here, and they were reproducing, well, like reproducing frogs, and eventually there were too many of them, and so they started to have limiting factors. There might have been not enough water or space or food or too many predators or a disease that went around, but the curve leveled off because of those limiting factors, and we can see that it's logistic growth. Now, as a reminder, a limiting factor is anything or any factor that limits the size or the growth of a population. And in doing so, it slows the growth and results in that stable population state that is known as carrying capacity. Now, there's two types of limiting factors. One we're not going to spend too much time on, but I wanted to refresh your memory. It is density independent limiting factors. And these are limiting factors that affect an entire area, and it doesn't matter what population you are or how many of your population are in a particular area. You are just kind of in the wrong place at the wrong time. So for example, if there's a forest fire and you aren't able to get out of the area, then that would be density independent. It doesn't matter how many birds or earthworms or humans or deer, whatever. If you were there and you couldn't escape, it doesn't matter how many of you were there. You were in the wrong place at the wrong time, and so that's a density independent. It doesn't depend on the density limiting factor. Some other examples would be like spraying herbicides to kill plants or spraying pesticides to kill bugs. And here's an example right here. Sometimes a population will suddenly crash because it's just such a catastrophic event. So it could be a forest fire, or here we're looking at the effects of weather on an aphid population. So maybe this was, there was a frost or something. And so we have this exponential growth. It might flatten out for a little while, or it could even suddenly decline. And so we've got this boom of this like increase, boom, explosion of the population, and then a bust. So rather than reaching or even staying at carrying capacity, the population size crashes. Now, the other type of limiting factor is density dependent, and that's what we're primarily going to talk about today. And of course, it does depend on the density of the population because it's density dependent. It depends on the density. But first I should define population density. It's the number of individuals in a particular area. So like in St. Croix County or in the city of Minneapolis. So for example, if we're talking about the city of Minneapolis, it has an area of 57.49 square miles. That's including the water. And it has a population of 425,403 people. So if we divide the population, the number of people, by the area in square miles, then we can see that the density is 7,334 people per square mile. So if you had a square mile and you divided up all the people equally, there would be 7,334 people. Hey, look, guys, it's my cat. Say hi, kitty. Meow. Her name is Pixel, as in like, computer pixels. Oh, yeah. I know you're excited to learn biology. Understandable. Mwah. All right, now if we're talking about Stillwater, and I'm not talking about the Stillwater School District, but the city of Stillwater, it has an area of about 9 square miles. I know, I thought it was bigger too. and a population of about 19,142. So if we divide the number of people by the square miles, then we have about 2,110 people per square mile. So if you've got that same square mile, then it's not as dense as the city of Minneapolis. Now, if you compare it to New York City, which is the most dense city in the United States, you've got in that 1 square mile 36,404 people. Like, whew, that's like that movie theater with 400 people, but a capacity of 100. Like, that's a lot. And then the second most dense city in the United States is San Francisco. And that has a density of 18,128 in that same little square mile. So of those three, you can see that relatively in Stillwater, we're pretty spread out. Oops, sorry about that. So the table below compares the density of each state. So you can see that the most dense state is the District of Columbia, followed by New Jersey, followed by Rhode Island, Massachusetts. You get the points. I highlighted some of the Midwestern ones. So in Wisconsin, it's 26th most populated. Minnesota is our most dense, I'm sorry. Minnesota is the 31st most dense state in the United States. Iowa is 37th. North Dakota and South Dakota are 48 and 47 respectively. And then Alaska is the least dense state in the United States. So density dependent factors are the second type, like I said, of limiting factor, and they don't usually affect small scattered populations as much as they affect large dense populations. And because they affect these large dense populations, they usually result in increased competition. So think toilet paper and protective masks. Now, when this all started, I heard some people say, like, I don't know why people are hoarding toilet paper. It's not like that's going to save them from the virus. That's true. But a lot of people knew that we were going to have to quarantine to some level, and they didn't want to run out of toilet paper, which, good idea. And so they ran out and bought up bulk toilet paper. And so the people were competing for the toilet paper, among many other things. Like, you can't get a bottle of Tylenol, even off of Amazon, because there's so much competition for these supplies that we consider necessary if we're not going to leave our house. So examples of density-dependent limiting factors include lack of a particular resource, so food, water, space, shelter, sunlight, toilet paper, predation, overcrowding, and of course disease. And that's what we're going to talk about because this is COVID biology. So in the case of an infectious disease like COVID-19, the more people that are in a particular space, the more quickly the disease is going to spread. So think about Stillwater with 2,100 people in that 1 square mile versus New York City, which has 36,000 people in that 1 square mile. You can imagine if one person starts coughing, that it's going to spread a lot more quickly when you've got 36,000 people in 1 square mile. And COVID happens to be an infectious disease that spreads really easily through respiratory droplets, and it can remain viable on different surfaces for quite some time. So for example, we cough or we sneeze or whatever, and the air droplets then are the virus is kind of like spewed out in respiratory droplets, and then those droplets can stay in the air and viable for 3 hours. Conversely, they could land on a different substance, for example, steel or plastic. So let's say that you cough in your hands, and then you go to Target and you grab the shopping cart. Well, the virus can stay on that plastic part on the shopping cart, or just the steel of the shopping cart, for up to 3 days. Ooh. Cardboard, about 24 hours, and glass for about 4 days. So, ooh. And if we look at the areas in which COVID-19 is most quickly spreading because it spreads so quickly and it can live on these surfaces for such a long time, we see some pretty amazing yet expected correlations. So, first one we're going to look at is the density of each state. So I just went and found this map here, and it shows where different states are most dense. So California is more dense than Texas, which is more dense than Iowa, which is more dense than South Dakota. So the darker the green, the more dense the area. So here's New Jersey, which is a very dense state, as we talked about before. Now, I went and grabbed this map on, well, yesterday, 3/29, because I'm making this video on Monday the 30th. So on Sunday, March 29th, I grabbed this, and OMG, like, you can totally see that the density of the state is related to how quickly COVID is spreading throughout that state. So in states like North Dakota, South Dakota, Wyoming, where people are really spread out, so if we're talking about like how many people per square mile, there aren't very many in those states. I don't know what the number is, but let's say that it's 500 in Wyoming per square mile. Well, then you're not coughing on your neighbor as often. You can see that Wisconsin has more cases than Minnesota because it's a more densely populated state. And the most cases, of course, are in the most densely populated states because whenever people are in close contact, it's easy to spread those diseases and infectious diseases, depending on how they're spread. But for COVID-19, since it's respiratory droplets, it's easy to spread. And then you can look even more closely at the density by county. And if you look at, like, you can see here's the Los Angeles area. Well, oh my goodness, that's not only the most dense area in California, or one of the most dense areas in California, but it's also where we see the most spread of the disease. Same with the East Coast. If we look at Minnesota, you can see that the metro area has the most spread or the most diagnosed cases of COVID-19, and it's also the most dense area in the state. So, science. I mean, like, it's mind-blowing and applicable, and we just all do it every day. So, speaking of doing something, you guys should totally go answer your questions on Schoology now. And if you have other questions or questions about the questions or whatever, give me a call or a text or an email, or I don't know, we'll get in touch with each other. So good seeing you. And I might not talk to you again until next Monday. So have a great weekend.